Ever wondered how AI systems handle uncertainty? Like when a self-driving car isn't 100% sure if that's a pedestrian or a tree. Or why some medical diagnoses might come with a maybe instead of a definite answer. Today, we're diving into a groundbreaking new approach to measuring uncertainty in machine learning, ones that go beyond the traditional coin flip model of probability. Let's start with the basics. In statistics and AI, we often use probability to quantify uncertainty. Think of it like a ruler, measuring how likely something is to happen. But here's the catch. Classical probability works great for aleatoric uncertainty, the kind of randomness you can't control, like the roll of a die. But what about epistemic uncertainty? That's the unknown unknowns, the gaps in our knowledge. Like what if the data we're using is incomplete or biased? Traditional probability models assume we have a single, precise answer. But in the real world, sometimes we just don't know. Imagine trying to predict the weather with a thermometer that's broken. Your probability might be wrong, but you can't even tell how wrong. That's where imprecise probability comes in. It's like using a flexible measuring tape instead of a ruler, allowing for ranges of possibilities rather than a single number. This paper introduces a new tool called the Integral Imprecise Probability Metric, IIPM. Think of it as a supercharged version of a classic statistical tool called the Integral Probability Metric, IPM. But instead of just comparing two probabilities, IIPM uses something called a Choquet integral to handle those fuzzy uncertainty ranges. It's like upgrading from a basic calculator to a quantum computer for uncertainty analysis. Here's the magic. IIPM doesn't just compare two models. It compares a model to its mirror image, what's called its conjugate. By measuring the difference between these two, we get a new way to quantify epistemic uncertainty. The authors call this the Maximum Mean Imprecision, MMI. It's like checking if your measuring tape is stretched or bent, helping us spot when an AI is truly uncertain, not just confident in the wrong answer. Why does this matter? Well, traditional methods struggle when there are lots of possible outcomes. Imagine a medical AI trying to diagnose 100 different conditions at once. Classical approaches might overrate their confidence, leading to dangerous mistakes. But MMI, it scales better and gives more honest answers. Think of it like this. Traditional probability is like a single path through a maze. But real-world data, it's more like a labyrinth with multiple routes, some blocked, some unclear. IIPM and MMI help AI navigate that labyrinth, accounting for both the randomness of the environment, aleatoric uncertainty, and the limits of its knowledge, epistemic uncertainty. At the core of this is a simple question. What does it mean for an AI to be uncertain? Traditional AI models often act like they know everything, spitting out a single answer with a confidence score. But real-world data is messy. Think of it like a weather forecast that says, 70% chance of rain, that's precise probability. But what if the data is incomplete, the sensors are faulty, or the situation is totally new? That's where things get tricky. There are two main kinds of uncertainty, aleatoric and epistemic. Aleatoric is the inherent randomness of the world, like the roll of a dice or a sudden gust of wind. It's unavoidable. But then there's epistemic uncertainty, the lack of knowledge. Imagine training an AI on a dataset missing critical information, like a rare disease no one's seen before. The model isn't just wrong, it's aware it doesn't know. Traditional AI often mixes these up, leading to overconfidence or blind spots. Enter imprecise probabilistic machine learning, IPML, a game changer. Instead of forcing models to pick a single probability, IPML lets them express ranges of possibilities. Think of it as a weather forecast saying, there's a 40–60% chance of rain instead of a rigid 50%. This approach is like giving AI a margin of error for its confidence, making it more reliable in uncertain situations. Two tools power IPML, credal sets and belief functions. A credal set is a cloud of probabilities, a range of possible outcomes rather than one exact number. It's like a map with multiple routes instead of a single path. For example, in self-driving cars, a credal set might represent all possible pedestrian movements, helping the car prepare for the unexpected. Then there's the belief function, which quantifies degrees of support for different outcomes. Unlike traditional probabilities, which assign exact values, belief functions let models say, I'm 60% sure this is true, but I'm also open to other possibilities. This is especially useful in tasks like medical diagnosis, where ambiguity is the norm. Researchers like Mohammed Hassan Shaker and Ike Hullermeyer are pushing IPML further. Their work shows how models like random forests can distinguish between aleatoric and epistemic uncertainty, leading to more robust decision-making. For instance, in climate modeling, IPML helps separate natural variability from gaps in our understanding of complex systems. So here's the thing, this approach isn't just a clever trick in the lab. It's a game changer with real-world applications that could reshape how we work with data. Let's break it down. First, imagine you're running a statistical test to spot trends in a dataset. Traditional methods can get thrown off by outliers, those wild, weird data points that don't fit the pattern. But this method, it's like giving the test a pair of sunglasses, cutting through the noise. It makes statistical tests more robust, so you can trust your results even when the data isn't perfect. Then there's generative models, those AI systems that create art, music, or even fake news. They're powered by probabilities, but they often struggle with uncertainty. This approach helps them acknowledge when they're unsure, leading to more realistic outputs. Think of it as teaching the AI to say, I'm not entirely sure about this part, instead of just guessing. And what about causal inference? That's the tricky business of figuring out cause and effect from messy, real-world data. Whether it's understanding how a drug affects patients or why certain policies work, this method handles imperfect data better. It's like having a clearer map through a foggy forest, still uncertain but way more navigable. Best of all, it's non-parametric. No need to force data into rigid boxes or assume it follows a specific pattern. It adapts, making it versatile for everything from climate models to social science. This isn't just about better math, it's about building tools that understand the chaos of the real world. And that's pretty exciting, right?